Welcome! In this session, we'll dive into a fascinating problem titled The Number of Weak Characters in the Game. This is a great opportunity to sharpen your skills in algorithm design and analysis. Stay tuned as we explore the problem, discuss strategies, and arrive at an efficient solution. Let's get started. In this problem, we are dealing with characters in a game, where each character is defined by two properties, attack and defense. These properties are represented as a 2D integer array called properties, where each entry corresponds to a specific character. For example, properties I equals attack underscore I, defense underscore I, tells us the attack and defense values of the ith character. Now, a character is considered weak if there is another character in the game with both a strictly greater attack value and a strictly greater defense value. Our goal is to determine how many weak characters exist in the game. To summarize, the input is the properties array, and the output is an integer representing the total count of weak characters in the game. To better understand the problem, let's look at an example. Suppose the input is properties equals 5 5, 6 3, 3 6. Here, we have three characters. The first character has an attack and defense value of 5, the second character has an attack of 6 and a defense of 3, and the third character has an attack of 3 and a defense of 6. For a character to be considered weak, there must be another character whose attack and defense values are both strictly greater. When we compare these three characters, we find that no character satisfies this condition. For every pair of characters, at least one of the properties, attack or defense, is not strictly greater. As a result, there are no weak characters in this example, and the output is 0. Next, consider another example where the input is properties equals 2 2, 3 3. Here, there are two characters. The first character has an attack and defense value of 2, while the second character has an attack and defense value of 3. When we compare these two characters, we see that the second character has both a strictly greater attack value, 3 greater than 2, and a strictly greater defense value, 3 greater than 2, compared to the first character. This makes the first character weak. Since there is exactly one weak character in this case, the output is 1. Now, let's analyze a third example where the input is properties equals 1 5, 10 4, 4 3. In this case, we have three characters. The first character has an attack of 1 and a defense of 5, the second character has an attack of 10 and a defense of 4, and the third character has an attack of 4 and a defense of 3. When we compare these, we find that the third character is weaker than the second character because the second character has both a strictly greater attack value, 10 greater than 4, and a strictly greater defense value, 4 greater than 3. The first character, however, is not weak because no other character satisfies the condition of having both properties strictly greater. Therefore, the output for this example is 1. Finally, let's consider the constraints and edge cases. The length of the properties array can range from 2 to 100,000, and each entry in the array contains exactly two integers. Both the attack and defense values for any character range from 1 to 100,000. Now, for edge cases, if all characters have identical attack and defense values, no character can be weaker than another, so the output is 0. For example, with properties equals 1 1, 1 1, 1 1, the result is 0. Another edge case is when the array contains only two characters, such as properties equals 1 2, 2 1. Here, no character is strictly weaker, so the output is also 0. Lastly, for large input sizes with values near the upper limit, such as 100,000 characters with attack and defense values of 100,000, the algorithm should handle this efficiently within the constraints. To solve this problem, we can consider two main approaches. The first is a brute force method. Here, the idea is straightforward. For each character in the array, compare it with every other character to check if both their attack and defense values are lower. If so, we classify that character as weak. While this approach is simple and intuitive, it comes with a significant drawback. It operates in n squared time complexity because of the nested loops, making it impractical for large inputs. On the other hand, the optimized approach leverages sorting and traversal to address this inefficiency. By sorting the characters based on their attack values, we can group characters with similar attack values together, and then process them in a way that minimizes redundant comparisons. This approach uses a greedy strategy to efficiently handle defense comparisons, which we'll explore further. To implement the optimized approach, we follow three main steps. First, we sort the properties array by attack in ascending order. If two characters have the same attack value, we then sort them by defense in descending order. This ensures that while processing, weaker defense values for the same attack are always compared against stronger ones. Next, we traverse this sorted array from right to left, maintaining a variable called max_defense to track the highest defense value encountered so far. As we process each character, we check if its defense is less than max_defense. If it is, we classify the character as weak. Otherwise, we update max_defense to the defense value of the current character. This method is far more efficient because sorting reduces redundant comparisons and the traversal step processes the array in linear time. The sorting and traversal strategy is chosen because it strikes a good balance between simplicity and efficiency. By sorting the characters, we structure the data in a way that eliminates unnecessary comparisons, and the greedy traversal ensures that we can efficiently determine if a character is weak. Compared to the brute force approach, this reduces the time complexity from O(n)² to O(n)log(n), thanks to the sorting step. While sorting adds some overhead, it is manageable given the constraints, and the traversal itself is linear in complexity. This makes the optimized approach highly scalable, even for large inputs, such as when the number of characters goes up to 10 to the power of 5. Overall, this strategy is well suited for the problem's requirements, offering a practical and efficient solution. To tackle this problem using the brute force approach, we need to systematically evaluate each character in the dataset to determine if it qualifies as weak. The definition of a weak character here is one for which another character exists with both strictly higher attack and defense values. First, let's think about how the input is represented. The input consists of a list of tuples, where each tuple represents a character, and the two integers in the tuple correspond to the character's attack and defense attributes. For example, if you have 5, 3, 6, 4, 4, 2, the first tuple, 5, 3, represents a character with an attack value of 5 and a defense value of 3. To solve the problem, we initialize a counter variable, weak_count, to 0. This counter will track the number of weak characters we identify. Then, we set up an outer loop to examine each character. For the character at index I, we extract its attack and defense values, which we denote as attack, I, and defense, I, respectively. The goal is to compare this character against all others in the dataset to see if it qualifies as weak. Now, for each character in the outer loop, we use an inner loop to compare it against every other character in the list. This ensures that we evaluate all possible pairs. Specifically, for the character at index I in the outer loop, the inner loop iterates through all other characters at indices j, where j is not equal to I. In this inner loop, we check the weakness condition. Does there exist a character at index j such that both attack, j, is greater than attack, I, and defense, j, is greater than defense, I? If this condition is met, it means the character at index I is weak. When this happens, we increment the weak_count by 1 and immediately break out of the inner loop. There's no need to search further for additional stronger characters since just one is sufficient to classify the character as weak. After both loops complete, we return the value of weak_count as the final result, which gives the total number of weak characters in the dataset. This brute force approach is straightforward, but it comes with a computational cost. The nested loops result in a time complexity of O(n)², where n is the number of characters in the input. For small datasets, this is manageable, but for larger datasets, such as those with tens of thousands of characters, the performance may degrade significantly. This highlights the importance of considering the algorithm's efficiency. Also, the weakness condition is worth emphasizing. For a character to be classified as weak, both its attack and defense values must be strictly smaller than those of another character. This ensures that we only count characters that are unequivocally weaker. Furthermore, the use of a break statement to exit the inner loop early when a weak character is identified helps avoid unnecessary computations, making the algorithm marginally more efficient within the brute force framework. We should also think about edge cases and how the algorithm handles them.
For example, if the input list contains only one character, the result is 0 because there are no other characters to compare against. Another edge case is when all characters have identical attack and defense values.
In this scenario, no character can be strictly weaker than another, so the result is also 0. Additionally, if the input list is already sorted by attack or defense, the brute force solution will still work because it directly compares all pairs without relying on the order of the list. Regarding data structures, the input is represented as a list of tuples, which is simple and easy to work with. The only extra variable we use is weak_count, which is a scalar variable for tracking the count of weak characters. This ensures that the space complexity remains 1, as no additional data structures are required beyond the input itself. The core operations of the algorithm are straightforward but critical. Each pair of characters is compared to check if one is strictly stronger than the other. This involves 2 comparisons per pair, one for the attack values and one for the defense values. These comparisons form the foundation of the algorithm. Additionally, the use of a break statement within the inner loop is an important optimization. Once a character is marked as weak, there's no need to continue comparing it with other characters, which saves some computational effort. To better understand how the algorithm works, let's consider an example. Suppose the input list is 5, 3, 6, 4, 4, 2. We'll walk through the algorithm step by step to see how weak characters are identified and counted. We begin by initializing weak_count to 0. In the first iteration of the outer loop, I is 0, so the current character is 5, 3. We compare it with 6, 4 in the inner loop. Since 6, 5 and 4, 3, 5, 3 is marked as weak, and we increment weak_count to 1. Next, for I equals 1, the current character is 6, 4. We compare it with 5, 3, and 4, 2, but in both cases, neither character is strictly stronger than 6, 4. Thus, weak_count remains 1. Finally, for I equals 2, the current character is 4, 2. Comparing it with 5, 3, and 6, 4 reveals that both are strictly stronger, so 4, 2 is marked as weak, and weak_count is increment to 2. At the end of all iterations, we return weak_count, which is 2. The time complexity for this process is n squared, due to the nested loops, while the space complexity remains 1, since no additional space is used beyond the input list and the counter variable. This implementation solves the problem efficiently using sorting and a single traversal. First, we sort the properties list by attack in ascending order, and for characters with the same attack, we sort their defenses in descending order. This ensures that while iterating, characters with the same attack are considered in decreasing defense order. We then initialize 2 variables, max_defense to track the highest defense encountered so far, and weak_characters to count the weak characters. By traversing the sorted list in reverse, we ensure that for any character being processed, all subsequent characters in the iteration have higher attack values. During the iteration, we compare the current character's defense with max_defense. If the current defense is lower, it means this character is weak, and we increment the weak_character's counter. Otherwise, we update the max_defense to the current defense. The overall complexity is determined by the sorting step, which is n log n, and the traversal, which is n. This makes the solution efficient and suitable for large inputs. Here, we begin by importing the necessary utilities and defining our class. The function number of weak characters takes a 2D array called properties as input, where each subarray represents the attack and defense values of a character. The first step is to sort the array. We sort by attack in ascending order, and for characters with the same attack value, we sort by defense in descending order. This ensures that characters with the same attack are grouped together, but those with higher defense come first. Sorting in this way helps us efficiently identify weak characters later. Next, we initialize 2 variables, max defense, which keeps track of the highest defense value seen so far, and weak characters, which counts the number of weak characters. We then loop through the array in reverse. By traversing backward, we can use the sorted order to compare each character's defense against the maximum defense seen so far without missing any potential weak characters. In the loop, for each character, we check if their defense value is less than the current max defense. If it is, this character is considered weak, and we increment the weak character's counter. Otherwise, we update max defense to the current character's defense, as it represents a stronger defense value for comparison in subsequent iterations. After completing the loop, we return the total count of weak characters. This approach ensures an efficient solution, as sorting the array and traversing it once gives us the result in optimal time complexity. By processing the array in reverse, we avoid redundant checks and ensure that the solution scales well for larger inputs. To solve this problem, we start by sorting the properties list. The sorting is done first by attack in ascending order, and if there's a tie in attack, by defense in descending order. This ensures that when we iterate through the list in reverse, characters with higher attack values come first. For example, given the input 5, 5, 6, 3, 3, 6, sorting it results in 3, 6, 5, 5, 6, 3. This ordering is crucial for our approach to work efficiently. Next, we initialize two variables. The first is max_defense, which keeps track of the highest defense value we've seen so far while iterating. Initially, it's set to 0. The second is weak_characters, which will count the number of weak characters. This is also initialized to 0. Now we traverse the sorted list in reverse. In the first iteration, we look at the character with attack equals 6 and defense equals 3. Comparing its defense with max_defense equals 0, we find that 3 is greater than or equal to 0. So, we update max_defense to 3. No weak character is found in this step. In the second iteration, we evaluate the character with attack equals 5 and defense equals 5. Comparing its defense with the current max_defense equals 3, we note that 5 is greater than or equal to 3. As a result, we update max_defense to 5. Again, no weak character is identified here. Finally, in the third iteration, we examine the character with attack equals 3 and defense equals 6. Its defense is compared to max_defense equals 5, and since 6 is greater than or equal to 5, we update max_defense to 6. Once more, no weak character is found. At the end of this example, the total count of weak characters remains 0. Moving on to the next example, we consider the input 2, 2, 3, 3, 4, 1. After sorting, the list remains 2, 2, 3, 3, 4, 1, because the properties are already in the desired order. We initialize the variables again, max_defense is set to 0, and weak_characters is set to 0 as well. Now, we traverse the sorted list in reverse. In the first iteration, we evaluate the character with attack equals 4 and defense equals 1. Comparing its defense with max_defense equals 0, we find that 1 is greater than or equal to 0. So, we update max_defense to 1. In the second iteration, the character with attack equals 3 and defense equals 3 is examined. Its defense is compared to max_defense equals 1, and since 3 is greater than or equal to 1, we update max_defense to 3. Finally, in the third iteration, we look at the character with attack equals 2 and defense equals 2. This time, comparing its defense with max_defense equals 3, we observe that 2 is less than 3. This means the character is weak, so we increment weak_characters by 1. The final count of weak characters for this example is 1. Now, let's consider another example with the input 1, 5, 10, 4, 4, 3, 10, 2. After sorting, the list becomes 1, 5, 4, 3, 10, 4, 10, 2. Again, we initialize max_defense to 0 and weak_characters to 0. Starting our reverse traversal, the first character we evaluate has attack equals 10 and defense equals 2. Comparing its defense with max_defense equals 0, we find that 2 is greater than or equal to 0, so we update max_defense to 2. In the second iteration, we encounter another character with attack equals 10 but with defense equals 4. Comparing this defense with the current max_defense equals 2, we see that 4 is greater than or equal to 2. Accordingly, we update max_defense to 4. No weak characters have been identified so far. In the third iteration, we look at the character with attack equals 4 and defense equals 3.
Comparing its defense with max_defense equals 4, we notice that 3 is less than 4. This means the character is weak, so we increment weak_characters by 1. Finally, in the fourth iteration, we examine the character with attack equals 1 and defense equals 5. Comparing its defense with max_defense equals 4, we find that 5 is greater than or equal to 4. As a result, we update max_defense to 5. At the end of this example, the total number of weak characters is 1. This concludes our walkthrough of the solution, demonstrating how sorting and a reverse traversal with attract maximum defense help efficiently determine the number of weak characters in the game. The time complexity of this solution can be broken down into two main components: sorting the input and traversing it. First, the sorting step has a time complexity of O, n log n, where n is the number of characters in the properties list. This is because Python's built-in sort function uses timsort, which is efficient and guarantees O, n log n, for sorting. The custom key used in sorting, lambda x, x0, x1, operates in constant time for each element, so it doesn't affect the overall complexity of the sorting step. Once sorting is complete, the algorithm then iterates through the list in reverse order to evaluate weak characters. This traversal is a straightforward linear pass, contributing O, n, to the time complexity. When we combine these two steps, the sorting step dominates, resulting in an overall time complexity of O, n log n. The space complexity of the solution is O1, meaning it uses constant space regardless of the input size. Let's break this down. During the sorting step, Python's sort function operates in place, which means it does not require additional memory proportional to the size of the input list. Any temporary memory used during sorting is minimal and does not scale with n, so it's considered O1. In the traversal step, the algorithm uses only two scalar variables, max_defense, which tracks the maximum defense value seen so far, and weak_characters, which counts the number of weak characters. These variables also require constant space, O1. Since no additional data structures are used throughout the algorithm, the space complexity remains O1. To understand how efficient this solution is, let's compare it to a naive approach. In a naive solution, we would compare each character with every other character to determine whether it is weak. This would require evaluating all n² pairs, resulting in a time complexity of O, n². For example, if n equals 10,000, the naive approach would involve 100 million comparisons, which becomes computationally expensive for large inputs. In contrast, the optimized approach avoids these pairwise comparisons by sorting the characters first and then making a single traversal of the list. This reduces the time complexity to O, n log n, which is significantly faster, especially for large inputs like n equals 10 to the power of 5. By leveraging sorting and a streamlined traversal, the optimized solution performs far fewer operations than the naive approach. Now, let's analyze the time complexity across different scenarios. In the best case, if the input is already sorted by attack in ascending order and defense in descending order, the sorting step still requires O, n log n, as timsort doesn't skip the sorting process entirely. The traversal step always requires O, n, so the overall complexity remains O, n log n. In the average case, where the input is randomly ordered, the sorting step still takes O, n log n, and the traversal takes O, n, so the complexity is unchanged. Even in the worst case, such as when all characters have identical attack values but differing defenses, the algorithm behaves identically, sorting takes O, n log n, and traversal takes O, n. In all cases, the sorting step dominates the complexity, leading to an overall time complexity of O, n log n. Similarly, the space complexity remains O1 in every scenario, since no additional data structures are used. This uniform behavior across cases demonstrates the efficiency and scalability of the algorithm. When tackling this problem, there are several common mistakes that can trip you up. First, skipping edge cases is a frequent issue. For example, you might forget to test inputs that are empty, have only one element, or consist of identical elements. These scenarios might seem trivial, but they often break solutions, leading to runtime errors or incorrect results. Another mistake is relying on inefficient brute force approaches. While these methods are easy to write, their time complexity, like O, n², or worse, can cause them to fail on larger datasets due to time limits.
Additionally, ignoring the properties of sorted or partially sorted inputs can lead to missed optimization opportunities. Sorted data often allows you to implement faster methods like binary search, sliding windows, or two-pointer techniques. Finally, misunderstanding the problem requirements is a critical error. Misinterpreting constraints like whether duplicates are allowed or what constitutes a valid output can lead to solutions that seem correct but fail to meet the problem's criteria.
Another area where mistakes often arise is in handling indices and boundaries.
Off-by-one errors, for instance, can occur when iterating through arrays or when distinguishing between inclusive and exclusive bounds. These bugs are subtle and can be challenging to debug, especially under time pressure. Now, when it comes to interviews, there are some key insights to keep in mind. Pattern recognition is crucial. Many problems boil down to familiar techniques like sliding windows, prefix sums, or dynamic programming states. Recognizing these patterns can help you move away from brute force approaches faster. Additionally, clarifying assumptions right from the start is essential. Always ask about edge cases, special constraints, or ambiguities, and confirm your understanding of the problem with the interviewer. It's also important to be ready to discuss the trade-offs of your solution, such as time versus space complexity or speed versus readability. A good strategy is to start with a brute force solution and then iteratively optimize it, clearly explaining your thought process at each step. Finally, test your solution thoroughly. Use diverse test cases, including edge cases and large inputs, to ensure your code handles all scenarios correctly. To deepen your understanding, it's helpful to study related problems that demonstrate similar techniques. For instance, the two-sum problem, LeetCode 1, is a classic example of using hash maps for efficient lookups. The longest substring without repeating characters, LeetCode 3, showcases how sliding window optimizations can be applied. The three-sum problem, LeetCode 15, is a great example of combining sorting with the two-pointer technique to reduce complexity. Similarly, the container with most water problem, LeetCode 11, highlights the power of two-pointer techniques for improving efficiency. Beyond these examples, you can also explore alternative approaches to solving problems. Brute force, for instance, involves checking all possible combinations or iterating through all elements. While it's straightforward to implement, it's often too slow for larger datasets. On the other hand, hash map or dictionary-based solutions allow you to store intermediate results or track scene elements, improving time complexity to O(n) at the cost of extra space. Another powerful technique is the two-pointer approach. This method works especially well with sorted data, as you can use two pointers to iterate from opposite ends of the array, reducing the search space efficiently. However, it does require the data to be sorted beforehand, so it may not be directly applicable to unsorted inputs without pre-processing. Finally, there's the divide and conquer strategy. This involves breaking the problem into smaller subproblems, solving each recursively, and combining the results. While this approach may involve a more complex implementation, it can significantly improve performance for certain problems, reducing time complexity to something like O(n) log n. Understanding when and how to apply these techniques and balancing their trade-offs is key to solving problems efficiently and effectively. Great job! We've successfully analyzed and solved the problem using an efficient approach. Remember, practice makes perfect, so keep challenging yourself with similar problems. If you enjoyed this session, be sure to like and subscribe for more engaging content. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!